Just wanted to do a quick review of these little step-down converters, DC to D converters you can get on Amazon and eBay, and little pretty cheap, pretty small modules, adjustable V out, V in, I think up to 28 volts, or it may depend on the module. Anyways, I figured they're advertised, the chip, if you look at the chip's data sheet, it's advertised as pretty efficient. See, you probably won't be able to get a good view of the chip. I'll link in below what it is in the data sheet. So I thought I'd get a couple, because I'm trying to move away from some older regulation ICs that I was using. So I populated a couple, and I was pretty surprised actually at first. I just for my current application, I was going to be doing something like a 12 volt to 5 volt step down, and without any load, just standby current. I don't know if you call it quiescent current because it's actually functioning. It was like something like 40-50 milliamps load, or I guess load, just quiescent current, I guess, if you can call it that. So we'll take a look at this one. This is the still the standard configuration that I got with it. So let me hook this up to the power supply, and this is just not exact measurement, not scientific, but just to give you an idea about. Alright, so we have the meter side hooked back up. Let's see if we can get this in one shot. We probably won't be able to. So let's hook up positive. Let's take a look at the power supply. I'm going to hook up the negative now. And we see we have 42 milliamps current draw, just sitting there. 5.1 volts on the output, and the module gets warm, mainly the inductor, from what I can tell. So I thought that can't be right. That's terrible. Both modules the same. I looked online. That seems to be someone. I'll link in somebody's article. They did a lot of testing on these. So I thought, this is pretty crappy. There has to be another. This can't be the chip itself. So the inductor was getting warm, and there was some talk as to though the inductor was a poor choice, although I don't think anyone had confirmed that. So what I've done here is I've had put on another inductor, and this is a 10 microhenry inductor that comes standard on these. And I just, looking around in my box, I saw that I had this inductor. I pulled off something, and this is actually a 100 microhenry inductor. So I thought, you know what, well, we'll just try something extreme at first to see if that changes anything. So let's take a look at this then. Alright, so we've got everything just about hooked up here again. Let's get this module out of the way. This is with the 100 microhenry inductor. Let's take a look at the power supply before we hook it up. Hooking up the ground to it now. And we can see we have 0 current draw now. And we have the output of 5.2 volts. So it's looking like the inductor selection is just terrible for the modules by default. At this point, I'm not exactly sure whether it's just the sizing of the inductor, which the datasheet I believe recommends a 10 microhenry inductor. So the 100 may be overkill. I have a 15 that'll also fit that I'm going to try here. Oh, that's a 47. Anyways, well, I have some 15s as well here. I'm going to try one of these instead on this module and see if that makes a difference. That'll show me whether it's the inductor itself that's a bad quality or bad choice, or the inductance value, because it is so similar to 15 microhenries is so similar to 10 microhenries that if there's a large change, it will basically mean that the inductor itself is just a bad choice. And I don't know if it's, couldn't tell you at the moment why, but we'll take a look at that and see, roll that plays as well. Okay, here we are with the 15 microhenry inductor instead of the 10. And let's see if there is still a problem with the idle current, no load. So I'm going to hook up the negative terminal again, and we can see that it does jump indeed right away to about 43 milliamps. So it's definitely, well, I can say definitely, it's probably not the inductor. It is probably not the inductor itself, but the value of the inductor on this particular board. So if I play with the trim pot and increase the voltage, the less difference there is, but in the input voltage and the output voltage, the quiescent current will actually go away. So, but you know, for my application, I wanted it to be 12 to 5 volts. So that's what we're using. That's what it's rated for. But it's just, you know, it's going to be terribly inefficient if it's drawing 50 milliamps with no load. So I might experiment with some other sizes. The 100 microhenry inductor does get rid of the current draw, you know, any measurable current draw from this power supply, which is, you know, not going to be too accurate, but nonetheless will give you a pretty good indication. Alright, so the next thing thought maybe would be useful is let's have a look at the data sheet for the chip and see if it describes something other than what we're seeing. So we can see it's the chip itself should be capable of 3 amp output continuous. Of course, I mean, you can read all this here, up to 95 efficiency under some specifications. So then we have a typical application circuit and an efficiency versus load curve with some predefined values. So we can see if what we're seeing is normal or not. And I can, you know, you can already tell that it's not going to be normal. You shouldn't be drawing 50 milliamps at zero load. So, I mean, that right away that would be completely horrible efficiency. Nothing like we'd see here. So let's have a little bit closer look here. So first, let's just have a look at the circuit here. We have the input, which is going to be right here. That's going to go into pin 2 directly. Okay, we'll have a look at pin 7, which is going to be 5, 6, 7 right here. No visible connections. This is just an enable line, so I'm sure it's pulled high somehow, maybe directly, but we can look into that. All right, so then soft start on 8. So here's pin 8. This I tested. This is no, this is 0.1 100 nanofarad, I believe, almost exactly. Let's see, 4 to ground. 4 is the ground. 5, we have the feedback. Okay, so here we have a 8.2K resistor, and when I checked, this seemed to be like a 30K pot. So, and it's not being used as a potentiometer, it's just being used as just a single variable resistor. And looks like the output is tied directly to one side of this pot, and ground is tied to the other side of this resistor. So then you basically have this divider here for the feedback here. So it's about what they show in the typical application circuit, except for this is kind of a little bit lower value. Instead of 10K, they've gone with 8.2K, but they probably did that for a reason. Pin 6, we have okay, so this is pin 6, and then we have this 3.9 nanofarad and 6.8. Okay, it looks, let me take a closer look, but it looks like they've gone with the 8.2 again, so that's kind of odd. And then here's your, I've changed this in this picture. This is the 100 microhenry inductor, but you know, they call for, in this typical application circuit, 10 microhenry only, which is what the module comes with by default. And then between boost and switch, we have a 10 nanofarad, so that's between pin 1 and pin 3. And I've confirmed this is this capacitor here. This is connected. So pretty much it all looks pretty normal so far. But then something that caught my eye is for the output and input capacitors. They want to use, in this, again, typical application, they specify 2x 22 microfarad ceramics on the output and the input. And I measured the capacitance across. Here's the output and the input and the output capacitors here. These appear to only be in circuit measure 10 microfarad. So really it's a quarter of the capacitance that they're asking for. So potentially this could throw the whole circuit, the whole switching off. When you're closing a switch and you may not have enough capacitance, you're going to be dropping the voltage a little bit, and you know, potentially the switching is just thrown off by this. So something to try as well would be to add some capacitance to the input and output and see if that makes a difference. Because we know that increasing the inductance helped. So that could have calmed the switching down a little. It would work at a kind of a lower switching frequency as well. So that's something to add. And here is the this probably up here is R4. So this is, yeah, look, here's a trace, here's a trace. That's probably going to go to 7 right here. So that's your 100K enable, 100K V into enable. So it looks like the circuit's pretty much very similar to what we have as far as the typical application. But if we look at the efficiencies under load current, we can get a better idea for what the chip should be capable of. So we're dealing with a 12 volt in, and under this diagram it's a 3.3 volt out. So actually I believe we should be able to do even better than this efficiency, which is extremely good, honestly. Under zero load, look what they're achieving. You know, almost probably 95% efficiency. So we have zero load, and you know, our efficiency is like I don't know, 0 or something. I don't know what it would be because there's no load and there's a fairly high draw. So so we should be probably looking at achieving at least 95% efficiency, because we have a higher V out than this 3.3 volt even. And it seems as though with the higher the V in and the lower the V out, the worse the efficiency is going to be, judging from this. So we should be seeing a lot better than this, and the circuit looks very similar to what they have here. So I'm going to try to add some capacitance and see if this calms anything down. Okay, so here we are. We're back on the bench, and I've added two 10 microfarad ceramic capacitors. 1206 is pretty big guys, honestly. These are good to 16 volts, I believe. They specify 6.3, but it shouldn't matter. So we can see now whether this is going to make a difference. We have roughly the same size inductor as came on here. Came with these 10 microhenry inductors. So let's hook this up and see if we get that 45 some odd milliamp power draw just off the out of the gate. So let's see, negative on this side. So we'll hook up positive first. Okay, and then we'll take a look at the power supply. Okay. And now I'll hook up the negative. And she's hooked up and it's not drawing any current. So that's interesting. So let's just take a quick voltage measurement here and see if we're outputting things, or maybe we killed something. Okay, so we finally have it all hooked up. It's kind of a little bit fumbly, but we're outputting 5 volts. And we are now drawing no current, so the extra 20 microfarads in capacitance total between the output and the input actually made the difference, apparently. So the low capacitance was actually throwing off the switching somehow. So that seems like it works. Next would be, of course, to try to load and see what kind of efficiencies we're seeing. I'll set up something briefly and maybe calculate some efficiencies for this, but I'm not going to use a whole lot of meter setup. But as you can see, these modules are pretty, they function very poorly straight out of the box. Unless you already have efficiency built into your circuit in which you're using this, you're going to have extremely bad performance from these. So that's just an easy way to fix them, is to add some capacitance. Alright, so let me turn the camera off and we'll just add a quick load and see kind of what figures we're getting. Alright, we've got everything hooked up now. We have the dummy load. We have the output voltage here that's actually hooked up right to the output. We have the current, measuring the current here, the output current, the input current, input voltage. So you should be able to come up with a very rough measurement of efficiency. And I don't actually know what this inductor I put on here is. It's probably at least rated for an amp. So so keep in mind, this is not a off-the-shelf inductor. So let's begin by increasing the current in increments of 100 milliamps. Let's see what we get. Okay. Very touchy. There's 9, let me use my right hand. So there's about 100 milliamps. We're drawing 45 here, and I'll do the power ratings in the end. Or maybe I'll print them below. Let's do 200 milliamps. We're doing about 200. Output voltage is still stable. Let's do 300. A little over 300. Let's do 400. About 400. Everything looks still stable. I'm just gonna, if this starts to cut out, I'm probably gonna end because it's unable to regulate, but it's still regulating very well right now. In fact, I probably should have trimmed this more to 5 volts instead of 5.1, but okay, there's 500 milliamps, half an amp. Everything's still stable. 600, still stable. 700, still stable. Back it off a little bit. Well, never mind. Let's go up. 900, still stable. Make sure this isn't limited. Okay, let's do an amp. Well, it's basically at an amp. So we're at an amp. Still stable. You know, let's keep going until it drops off or the inductor blows up. 1.1. 1.2. Jeez. I think I'll go down an amp and a half. 1.3. And then we'll let it wait for a second. 1.4. 1. Uh-oh. Getting bad. Bad sign of things to come. Amp and a half. Voltage still quite stable right at the output. You know what, let's go to 1.8. That's what the module's rated for. It should drop off if it's too much. .8. I kind of doubt my inductor's rated for 2 amps. Ooh, it's hot. Okay, we're gonna call it there. It's still stable though, so quite stable now. Pretty nice. And then let's take a look at the efficiencies. All right, last thing here. Let's look at the efficiencies that were calculated from those measurements. So we have the VN, the IN, the power from that, and then we have the V out, the I out, the power from that. Through the miracle of calc software, we can easily calculate efficiencies and plot them. So here we have the plot, and you can see at that's at 200 milliamps, we're doing over 96% efficiency. And of course, this is all based from, you know, the input power is based on my power supply. So I don't know about the accuracy from that, but you know, it's seems, you know, fairly good. And then here's some other independent testing that I found online. I'll link in this article. He does a lot of testing. Let's just look at this graph here, because this is without the capacitance added. So we can see how much things were helped, because I didn't calculate any efficiencies before when things were obviously very wrong. So if we're looking at 12 volts in and 5 volts out, like I'm using in my test, we see we didn't test at 20 milliamps, which very poor efficiency, of course, because we're drawing almost 50 milliamps at just load. So yeah, very poor efficiency. Then we go up 50 milliamps, we're getting a little bit better. Of course, it's going to get higher. It's going to be slightly more efficient. I guess that's what I would imagine, and that's what we're going to see here too. 100 milliamps, we're looking at probably something like 48% efficiency, and that was my first point here. So we're looking at 95 versus 48. So it looks like adding this capacitance really did a large amount for the efficiency of this module. We go up to 250. I didn't measure specifically 250, but you can see his measurements are getting more and more efficient as as the current is increased. So, and then up to 500 he measures, and he's doing about like 72 at 500, out 510 doing about 93. So, you know, much better all across the board, especially at very low loads. So, yeah, and he calculates all kinds of efficiencies and all kinds of different things just for this module. So it's pretty nice article. You know, and what I think I found this just trying to look at to see if anybody else had these problems with the module, and yeah, they had. So I'll link this in. This is pretty useful. But then another thing we can look at is the data sheet again, see if our efficiency curve is something near what they're reporting. So we go look at this again. This is, of course, the 3.3 volt out, and the we'll be looking at the 12 volt in. So we can see that it looks pretty similar. We're doing, you know, they have a nice smooth curve. I don't know what increments they're testing at. I'm not testing at too many increments, but it seems fairly similar. We're seeing some good high efficiencies. Here's probably about 95, so we might jump into 96s. So we're maybe seeing, you know, something very similar to what they're seeing here. Apparently the scale goes to 10 amps. Let's see, 1 amp. You know, they're doing mid 90s efficiency at 1 amp. So at 1 amp, we're doing, you know, basically mid 90s, maybe low 90s. So looks like maybe slightly under their efficiency curve. So it's fairly linear, a little bit worse at the very low end, but it's still, you know, anything in the 90s is great. Even in the high 80s is great. So here we have a little drop. I don't know, I could try to recalculate that. There could be some problems here with maybe the inductor. I'm not exactly sure. So yeah, that's the efficiency under load. So this is looking actually very good, just adding capacitance. So it looks like, you know, the makers of the module either didn't test or decided that it was the 10 microhenry capacitance, 10 micro farad capacitance was enough, and perhaps, you know, they tested with capacitance already in the circuits. You know, if you have already input capacitance here, then you might not need this. So, and that's another thing for people with their own circuits. If you add input capacitance, which it's most likely going to be the reason behind this. I'm not sure about the output capacitance, maybe. But so if you already have capacitance built in on either side, maybe it'll work just fine. Otherwise, if you're kind of using it standalone, you're going to want to add some capacitance to the circuit. All right, well, hopefully that helped you, and I'll see you next time.